Carina, thank you so much for joining me today.
Thank you so much for having me.
All right. You are working on the mathematics plus AI, and it's one of my all-time passions, loves of life. So I'm very, very excited to chat about it. All right, let's start with the premise of what you're working on, self-improving mathematical superintelligence. So as for starters, can you explain in plain English what that is?
Yeah, 100%. So first of all, there's mathematics and there's superintelligence. When it comes to mathematics, it's everyone's favorite topic nowadays. AI systems just won the IMO Gold medal this year, and actually many AI systems the same time won the medal. Um, People are seeing large language models getting better and better at reasoning, and reasoning is broadly defined as math and coding. It makes sense to define it this way because, in fact, math and coding are the two pillars of the digital world. And quoting Eric Schmidt's, we have seen large language models have incredible gains over coding in the past year, 2 years or so. On the math side, however, it's sort of less invested in, and it's for a reason. Currently, large language models train on chain of thought reasoning. So for every math problem, they will have experts to describe the chain of thought and then train on those data. On the other hand, when it comes to coding, it's not quite just that. They will, for example, train on executable computer programs. So you can either see a check mark telling you the code has compiled successfully or there is an error message. So because of this difference, we see coding being a verifiable domain has had incredible gains versus for math, the verification comes from problems that have one numerical answer instead of a whole proof. So all the problems that have, pretty intricate logical reasoning get reduced to the final output. And Axiom is working to change that. We want to turn math proofs into computer programs. And using similar techniques in reasoning and in the development of coding, we can make really significant breakthroughs in the domain of mathematics as well. So that's mathematics. On the topic of superintelligence, why we call it superintelligence, it's not just a hype word. We define superintelligence as AI system that can generate new knowledge. Instead of just answering questions the user put in, we imagine the system to be your collaborator, co-author, AI scientist, AI mathematician. And the important defining characteristic is the ability to generate de novo new knowledge. Currently, we will pay experts from data labelers like McCord and Turing to write Olympiad math problems. In the future, hopefully, the AI system can tell you, hey, these are the math questions that are worthy to pursue. So combining the two, Axiom is building toward a system that can prove, conjecture, and make discoveries at an unprecedented scale and speed. And therefore, we think it's really exciting to be building mathematical superintelligence.
That's amazing. The premise, as you mentioned, is just incredible, and the entire digital world is built upon this. Can you can you talk about the the similarities and differences when it comes to applying AI for coding versus using it for mathematical proofs? So where can we use common fundamentals, and where does it start to diverge, where we need a different system to build like proofs that can be verified by the
Yeah.
mathematicians?
Yeah. So I say when it comes to turning math proofs into computer programs, there is one good news and one bad news. The good news is in coding, you have Python. These are programming languages. There is a programming language for proofs. It's called Lean, Lean. And Lean, after many years of development, I think since almost a decade ago, it was first developed at Microsoft. And now there are so many groups working on Lean. Lean 4 has become widely accepted and celebrated in the community, and it's also a lot easier to use as just a matter of fact of engineering um, um, efficiency, and so therefore because of a theorem called Howard correspondence, for every mathematical proof once you turn it into the language of Lean, because of how Lean is set up and there's a lot of dependent type theory behind it, you can actually run the mathematical proof. So that essentially turns this into a programming language related problem. Now, the bad news is, well, there are more than, I think, 1 trillion tokens of code on the internet, that's free for folks to scrape. There's a data scarcity problem here. Data scarcity for Lean proofs. There are at most, I think, 10 million tokens of Lean code. So you're seeing about 100,000 times data gap. This data gap is difficult to work with in an era of scaling. We want to close this data gap. And at Axiom, we are trying to have an internet scale data set for Lean math proofs as well.
Yeah, Lean is yeah, it's incredible how much progress has happened, and we'll touch upon that. Now, when you look at an AI system proving something, and if you have to explain that to somebody who's not from mathematics or coding, like what's an analogy, or how do you explain how AI proves things? How does it work?
Yeah, yeah, I think so. Are you talking about maybe like the Lean part or the general AI proving part?
Actually, let's do both. Let's start with the general AI proving part. Like, let's say you want to arrive at some mathematical proof. Like, how does it know how to navigate? Because the number of possibilities in a combinatorial explosion can happen. So, how does it prove that? And also, maybe an implementation. How does it happen inside the Lean language?
Yeah, 100%. I think if you look at, for example, the K-12 education system in middle school and high school, a lot of the math problems we encounter are fill in the blank kind of questions, like count the number of apples that satisfy certain property. Now, when you move to college, real mathematics, the ability to think in proof-based language is an important milestone for development of mathematical capability. In fact, at many universities, there is a class called Introduction to Proofs. We have been trained in a way, humans have been trained to write two-column proofs, mostly starting point in college. We will make certain assumptions and then deduce logically based on those assumptions the next step. So it's almost reducing the original problem to a new problem, an intermediate state, an intermediate goal that we would try to prove. So that's actually, it's backward and forward conjecturing. So it can either be, hey, I have this problem, and if I don't prove this, then there's no way I'm going to prove that. So that's backward deduction. Forward deduction is, given the conditions provided by the problem, what are some immediate things I can say about, say, the property of this set? And so if I can say that all the sets that satisfy the conditions this problem describes have another property, then I then get a bit closer to, from my point of view, from my point of knowing nothing, to the problem statement. So that's forward deduction. So in the sort of backward and forward deduction, eventually this gap close, and bingo, you have proved the thing that you're asked to prove. So that's how humans work on proofs. Currently, in a general informal language, natural language AI system, we will see ChatGPT, for example, telling you the step-by-step walkthrough of how a proof should be. The problem is, however, there's no way, unless you are an expert, to know exactly whether it is true or not true. And you also don't pinpoint a step where it starts to become problematic. That's why a lot of mathematicians don't trust the output of general large language models. On the other hand, when it comes to Lean, its functions more similar to Python than to natural language English deduction. We see the program start, defining new objects that show up in the problem statements, how you would define things in Python. And then it will continue building on little sub goals, just like how a human mathematician would deduce. And then eventually it will prove the desired statement, and you will see the complete code. Then you run on the code to see either it compiles a check mark or an error message at, say, line 37, which you then look at it, oh, what is going on? And you try to debug. So that's quite interesting because for the first time in human history, well, mathematicians have been working on logical reasoning, rigorous logical reasoning using pen and paper for thousands of years. Now we can digitalize the process of mathematical proofs and bring that closer to programming language that we're familiar with.
Right. That's amazing. Love the chain of thought here. Um, you are very accomplished in mathematics, and there is so much more to go. So I would love to maybe take a second to just talk about. No, we'll talk about how machines do it, but you as a human, can you just walk us through your first exposure to mathematics, the earliest thing you can remember, and also today, how do you look at a problem? What do you do? Like, how do you start attacking it? How do you break it down? How do you build a solution?
Yeah, 100%. So I love math. Like for as long as I can remember, when I was 8, I would go to these sort of mathematics Olympiad classes and work on really interesting and creative problems that's beyond the school curriculum. Then I kind of went along in the Olympiad math system and eventually went to MIT, where I surround myself with like classmates that are IMO gold medalists in their respective countries. And I'm like, oh man, I don't know math at all. But then an interesting sort of transition happened where we are Olympiad math problem solvers to research mathematicians. So there are two kinds of mathematicians broadly. One is really good at problem solving. The other one kind is really good at theory building. They will connect the dots between different disciplines, formulate new hypotheses and new conjectures, and then either invite their collaborators to solve it or try solving it themselves. So the ability to go broadly, read a lot of the literature, and then to connect the different dots, the theory building ability is really fundamental to the development of mathematics. That's how new fields are being proposed and discovered. And then you also need the problem solvers, obviously, to try to fill out the gaps of, oh, wow, okay, there are 12 conjectures because of the introduction of this one interesting definition. Then how do I prove these 12 conjectures and then push beyond that? It is a collaborative effort between mathematicians of different skill sets. So at MIT, I try to learn how to be a theory builder, and on top of having trained to be a problem solver. And that is quite interesting because if you look at large language models today, they're really good at problem solving, but they don't propose new hypotheses and conjectures, or they try to, but you have no way to verify that. So that is the question of intuition and taste. How do you know if the chatbot is telling you a definition that is worth investigating further into, or something that just made up by pattern matching? Now, what Axiom wants to do is we want to, through formal reasoning and informal reasoning combined, have one system that not only prove, but also conjectures and theory build. And that's quite exciting because, for example, the ability to introduce new definitions into the knowledge base, library learning is traditionally hard. So we're very excited to be working on these stubborn technical challenges. And on your question about how a mathematician will think about a problem, so we don't just compute the numerical output. There are many intermediate states that we need to travel to before we arrive at the final answer. And in that process, we are doing proofs. We are trying to prove lemmas one at a time, and then do hierarchical planning of bridging these different lemmas, almost like Lego bricks, to form a complicated proof. Now, this is a complex multi-step reasoning. Humans do it by either having seen similar things, which is pattern matching, or by just using the deduction ability. What is try to think, you know, uh, by different. It's almost like a tree search. Like what are the 5 possible ways of moving forward? We also do a lot of sanity checks. For example, we have this lemma that we think could be useful. Then immediately in our brain, we construct either examples to boost our confidence about this lemma or counter examples that tell us that, well, actually it's just not true and you should go another path. And then you can backtrack from there. All these are relevant in developing an AI mathematician.
Amazing. With that, I would love to dive into the engine room. So you founded a company called Axiom that you mentioned. You raised a big round, and congratulations on that.
Thank you.
Now you mentioned that the data is one of the limiting things. Like for example, as compared to the trillions of tokens available for average like text generation, mathematical proves there just isn't enough data. So when you look at the raw ingredients your system needs to think and reason, um, is data the real bottleneck? Do you have enough compute available? Do you have people? So can you talk about what the bottlenecks are and what you need to get to the next big breakthrough?
For sure. Uh, so I think for building an AI mathematician, we need a few things. One, we need data. We need a really large lean data set beyond what is currently available. And then we also need good lean infrastructure. So, for example, if you want to run anything on lean, it can be slow and buggy if the infrastructure isn't set up right. We also need a lot of strong engineering execution um, for example, building a knowledge base of all the lemmas and proofs that's currently available. So if you think about all the archive papers, how can you sort of, translate them or auto-formalize them or formalize them into the lean digital data set? We believe a citation-based knowledge graph is important, and we are doing large scale engineering to do that. So there are like it's a multi-component process. We have some amount of funding that we think are going to support our compute need and also talent need. We have the strongest team one can possibly imagine, coming from AI, programming language, and mathematics. We have word experts and out of one for each of these three fields coming together to build towards this dream and mission. So we feel really, really happy about that. And then it's really about just execution. We want to be very fast to sort of climb to the frontier, qualify SOTA of harder and harder benchmarks. So yeah, so that's kind of the setup.
Now, your when your AI system solves a problem, I mean, you give it a problem and it has to navigate and check different paths and build a solution. So how does it check its own work in plain terms? Because you don't want it to go on a wrong path too fast, too deep before knowing it's wrong. So how does it check?
Yeah. So there again informal reasoning system and formal reasoning system. The formal reasoning system side is it's quite simple. Frankly, you run the proof. You run the proof and then you see if it compiles. The setup of Lean as a programming language allows us to do that, and that's just incredible. On the informal reasoning side, typically people have tried to use LM as judges, so a judge system to critique bot to say, okay, well, here is potentially problematic. When you have a large group of large language models judges instead of a verifier, you have then a stochastic verifier, and that is able to give you some signal. We like the formal verification path, but by a lot, we think it's underinvested, and is also going to be more simple efficient.
And you mentioned self-improving mathematical superintelligence. So, what does self-improvement look like on a day-to-day basis when you're building this? Is it practicing on harder problems? Is it solving more number of problems, or is it like learning new techniques automatically? Like, what does that look like objectively?
For sure. Um, if you think about a system that can reflect on its own mistakes and also the correct answers, and then build these knowledge back into the system, the skills library, and then apply that the next time, that is how humans learn, for example. Like I would think about the mistakes I have made in my past life and reflect on them and then try to do better next time. So for the AI mathematician system we are developing, um, we are having the model reflect on its mistakes and then also reflect on what has worked successfully. And just like I point everyone to a really good paper called Lego Prover, it is the idea where you have an evolving skills library, and then you want to have all the things that you sort of new skills and new knowledge that you um, obtained from each attempt back into your skills library and then be applied the next time. Our system have interesting mechanisms designed to do that, relating to long-term and short-term memory. And without kind of going too much into the technical nitty-gritty details, we by having the sort of like skills learning design, it is self-improving. And also, quite interestingly, if you have another model in the same system that conjectures, that is able to propose math problems quite well, then the conjecture and the prover are actually forming one self-improving loop. The conjecture will set harder and harder curriculums based on the prover's performance, and then raise the bar for the prover to do better next time. And also, the conjecture could set curriculums that attack the vulnerabilities of the prover system. This sort of adversarial loop is quite interesting to build a self-improving AI.
And to solve the data shortage problem, and when it comes to just lean code available, one possible, and you tell me if it's reasonable or not. People are using synthetic data. They just they generate data in different domains. So in this domain, if you just have a code gen model generate, I don't know, a billion lines of lean code by solving many, many different problems, can that serve as additional data, or is it not structurally adding anything new to the system because it's the system that generated the code in the first place? So how do you think about synthetic data
Yeah,
here?
for sure, for sure. At Axiom, we take very bold synthetic data bets. We sort of invest heavily into having a large internet scale data set. And we do need synthetic data best to work to scale
Mhm.
because there is only so much that human experts can provide you. So now, for example, the running market quote for each IMO problem could be hundreds of bucks each problem. And that's just very hard to scale. Um, I think that for synthetic data to work, we need a verifier. It needs to be a verifiable domain. Otherwise, it's a bit hard to, if you think about large language model generate like synthetically all the human dialogue data, it's very hard to like know if they are like usable or it's just going to be trash when it comes to training.
Right.
And for example, coding though, if you have a program that compiles, that is quite valuable. However, you have certain challenges. For example, the signal could be sparse. That means if I try to, when the model has not seen much link yet, when it tries to generate synthetic link programs, it might not compile. It just might not. Especially when the proof gets really long. So to have like executable link code, that's a challenge in itself. Um, we believe in kind of two ways of getting synthetic data. One is through auto-formalization. There exists really amazing mathematical literature of the past like hundreds of years on journals, textbooks, archive papers, etc. If we can formalize that synthetically into lean code, and then we know that, first of all these mathematics are correct, right? So you have these, most of them are correct, unless, the referee doesn't catch some bug in the paper. You can then have quite interesting and high quality mathematical content in link. So that's auto-formalization. And once you kind of plant the seed data by auto-formalization at every difficulty level, we at Axiom believe that you can synthetically expand that to a much larger data set. 100 times, 1,000 times it.
And when it comes to measuring the performance and progress of the system, like what public benchmarks or challenges like do you care about? Like what is there? I'm sure there is something, but what do you care about?
For sure. There are many benchmarks in the formal mathematics community. Very ancient one is miniF2F. Now, miniF2F is basically completely solved. I believe that there is at least one model, if not two, that get 100% is saturated. And part of the reason why it could be saturated is maybe some folks have, data contaminated. It's like maybe have trained on it. It has been like around for many, many years. And there are other newer benchmarks called conjecture, for example, a benchmark collection of many years Putnam exam. So that's CombiBench. And there are other interesting benchmarks that are supposed to test the model's mathematical capabilities. So CombiBench is testing the combinatorial ability of models. And combinatorics problems are generally quite hard. If you look at the one unsolved problem of this past year's IMO, it is a combinatorics problem. And you look at the two problems that were unsolved last year, the IMO silver medal performance by Google DeepMind, I think both of them are also combinatorics problems. So somehow AI models just like not that great at combinatorics. And CombiBench intends to test that 100 problems are combinatorics, quite hard and high quality and de novo. There's also this newer benchmark called miniCTX V2, or I mean, the people using the version 2 of that benchmark. It's for long context reasoning, testing for the ability requires of a research AI mathematician that you need to be multi-step and kind of long context, and requires sort of beyond the Olympiad math solving abilities. We believe these benchmarks are great. We like to test our models on holistic, many benchmarks to see where it's doing well, where it's not. Um, one benchmark is a bit sort of thin as an evaluation metric, so we like to put the model to test on a lot of benchmarks, and we will also in the future roll out new benchmarks for the community as well.
You made an interesting observation that combinatorics has been hard for some reason.
Yeah.
Any, why is that? I mean, if you look at all the different fields, number theory, the topology, field theory, combinatorics, there's no reason specifically one has to be harder than the other, especially when it comes to an AI system, but yet it is. So how do you explain this?
Yeah, 100%. I have some uneducated guesses as a mathematician. Um, well, in other domains such as algebra, you look at the logical reasoning chain of thought in the proof. Um, the gap between one step to the next is quite small. And perhaps the similar pattern of deduction has happened in other similar problems as well. So whenever you have a Diophantine equation of say like, um, ax to the n plus by to the n equals cz to the n, you will try to, and x, y, z are required to be integers. You will assume x, y, z are the greatest common divisor is 1. So that kind of standard tricks really exist in a lot of problems. In combinatorics, however, there's more creativity required. The leap from one step to another is quite large. That's why what people call them aha moments is like, aha, I don't actually know how I could think of that, but somehow I did. A lot of the combinatorics problems, especially at the IMO and Putnam level, require that sort of eureka moment and creative thinking.
Mm,
So that's a little bit
right.
harder to pattern match. Um, and each problem is quite designed to be quite different. And that's one reason. Another reason I would say is combinatorics problem involve a bit more multimodality part of mathematics. That's quite interesting because if you look at math and a lot of problems involve symbolic expressions. Now, symbolic expressions are based on text. You have formula, equation. For combinatorics problems, you need sometimes graphics. A lot of combinatorics problems are set up as a chessboard. You have a grid now. Okay, this grid is a little bit hard to represent. You will
Right.
probably express the grid on a computer different way than literally drawing a grid. But then the visual and spatial reasoning components are lost in that translation. Graphs, for example, graph theory, a really big part of combinatorics and connected to many other branches of combinatorics. You look at the graph and then you try to add a line, or you erase a line, you perturb the graph. All these structures are a bit lost. That's why also geometry requires a whole different engine to solve. So for all the Olympiad math contests, generally alpha geometry is different from the alpha proof system. And in this past year's IMO, there are other teams using different geometry engine to solve the Euclidean geometry. Similarly, because of the visual component of the problem.
Interesting. So it's whenever you need multimodal, like combining different ideas from different subdomains to build a solution, it becomes a little bit harder versus like if you can solve in a self-contained subdomain where it can just go from start to end in one
Uh,
go.
yeah, I think generally if you see like the problem having C figure 1 and then there's a figure drawing, you'll be like, oh, like it might be.
Right,
Yeah.
right. Interesting. And so on the flip side, then something like algebra would be like AI would crush something like that. What? So if you had to pick, a couple of domains where AI has absolutely crushed it within mathematics, like what are those?
AI has absolutely crushed. I don't think AI has absolutely crushed any domain yet, quite interestingly. I
Oh,
think AI
interesting.
has I
Hmm.
think AI has crushed the domains it has seen. So
Ah,
specifically, if
okay.
you
Right, right.
AI a math problem that it has seen in its trainings, that likely it's gonna do well.
Hmm.
Um,
Interesting.
we see large language models repeatedly doing retrieval, looking up from the textbooks what are arguments that could be applied here.
Right.
Sometimes it's actually not the problem, but sometimes it gets it. For example, I think
Hmm.
recent there are those problems that were previously marked open,
No.
but then are
Yeah.
actually not open
Right.
because it has already existed in some German mathematicians, sketch paper, for example.
Right.
Um,
Right.
we at Axiom want to create AI mathematicians that can solve problems it has not seen
Hmm.
using formal and formal reasoning. And we think that is an incredibly ambitious goal. But
Yeah.
having an AI system that can consistently and correctly solve all branches of mathematics like algebra, analysis, number theory, and especially real research mathematics beyond IMO benchmarks that are competition for very bright kids.
Right.
We think that's really interesting.
Amazing. Now let's move to infra and compute, because what you're taking on a massive problem, and the infra footprint, I can imagine, is as you do more and more, it's going to be big. So as a
Sure.
starting point, can you talk about your compute footprint today as you're building the first big version of this?
Yeah. So we believe that to do this project well, we need scaling. We also need great sample efficiency. So I think it's like, as Percy Liang famously put it, is really multiplying these two axes. We believe that this is going to be an effort that needs a lot of compute. We are currently using our compute very smartly, and then we expect to scale as it goes.
Right. And are there parts of the stack that you had to build yourself because nothing worked off the shelf? Or how do you think about roughly what can you use off the shelf versus stuff that you have to build yourself?
Yeah. While we try our best to reduce the amount of infra we build in-house, we actually build a lot of infra in-house. So,
Right, right, right,
we, for example, spend a lot of, engineering cycles on lean tooling. There are a lot of tools from the open source community, but while those are interesting inspirations as to what tools are needed, they might not be sort of industry strength quality. So instead of, for example, fixing potential bugs in these tools, we'll build all these lean tooling ourselves in house. That's one big part of infra.
right.
Um, and there are other parts, for example, just reducing a lot of the very concrete research ideas into an engineering problem. We would
Mm.
love to have generalist engineers join us to build those out. For the compute part, we kind of take a similar approach from a lot of other startups, right? When we are really small scale, we use on demand, like buy as you go, pay as you go compute. And then when we scale up, we will probably have more kind of fixed term contract with compute providers that can also help us with a lot of the necessary infra, but also handle some of the infra related to training ourselves.
And as you productize this what you're building, AI Mathematician, where are the initial use cases that you're envisioning? Is it in research labs, finance, engineering, somewhere else?
Yeah. So I like to take tours at the Computer History Museum just on some of the days I enjoy just wandering around. In the history of Silicon Valley, there hasn't really been a case where there is a step function change in technology, but there is an absence of business model. This is something that, yeah, that we strongly believe in, and we also believe that there has been, obviously like bad execution of a sound business model that then, make the entire thing not able to work out. but we believe in a lot of applications being unlocked because of the fundamental phase transition of the technology. And some very initial ideas are formal verification of hardware, formal verification of software. So that is very much tied to the formal math system we're building. Because if you are like an informal math model, you can be really strong in math, but it cannot do formal verification well in these safety critical applications. Protocol verification and cryptography is also very interesting. And when you can do math consistently, correctly, you can also unlock, for example, finance, engineering, requiring, like, for example, complex differential equations, optimization, and many more.
Can you quickly explain formal versus informal verification?
Yeah. So informal side is not quite verified. It is, the stochastic verifier of large language models. They will have, large language models serve as judges. The formal verification side is one key part is the theorem provers like Lean that we're relying on.
Right. And when you look to the team you're building, you talked about what kind of people are joining, are about to join. So, how do you think about constructing a team here? Just maybe double click on, is it pure mathematics, systems, formal methods, infra, engineer? You need a bunch of superstars to join here. So maybe talk about what do you need to ship this.
Yeah. So we believe in three important pillars: AI, programming languages, and math. We believe in having folks with decades of experience in each of these pillars to come together. On
Right.
the AI side, you need amazing applied AI engineers and researchers. On the programming language side, we really have, I think, one of the best teams in the world applying machine learning to programming language and this like AI systems flavor of folks. Um, and then on the math side, we want mathematicians who are also hands-on engineers to work together with the team to have these mathematicians ideas, put them into engineering deployment.
And let's say you build this, you ship this, and it's starting to work. Now, once the AI mathematician system is live, can you talk about uh, throwing more compute or hardware? How does it make a difference? How quickly will it make a difference? Because if you give me a system and I show up with a massive GPU cluster, will I be able to do a lot with it? So can you talk about how the
Yeah,
system can scale with compute and infra?
yeah. We believe scaling law also works in this domain. We don't necessarily see any fundamental issue why it shouldn't. Um, there are, for example, difficulties and bottlenecks on the infra side, especially when it comes to lean. But those are not sort of insurmountable challenge. I think we fully expect scaling law to work pretty well here. And in fact, perhaps with greater impact because it's really the sample efficiency is going to be better.
And uh, if Axiom fully works according to what you have, your vision, what would be the biggest delta in the world? Like, what would become cheaper or faster or better in the world in a way that everyone would notice? Like, what are you expecting to see in the world?
Yeah, I think I would love folks to imagine AI goals at your fingertip. So deploying many AI mathematicians into all the complex systems that are currently not theoretically understood. These systems are quite complex to make sense theoretically, but then having an AI mathematician working together alongside with the applied scientist, we think that's going to be a game changer. And specifically, when the price of reasoning becomes more elastic, there is more demand. Javon's paradox is our opportunity. We expect to see new markets, use cases being unlocked because of the surge in supply of outlier mathematical reasoning capabilities. And
Right.
so, for example, if you can think of a hedge fund now being able to afford the best and scout the best AI mathematician as quant traders in markets that previously were not unlocked because, say, the total trading volume just too low for the unit economics to make sense because employing a really smart human quant that costs a lot of money each year. Like, what would that hedge fund do, and what would that market be like? That's a question of mass intelligence. If you think about, say, a cloud compute provider now having AI engineers to work on the routine IT optimization task, right? And these AI engineers are of the caliber of, say, Meta, the strongest Meta AI engineers. They're currently being paid, say, like 1 or 2 millions a year, right? How would that change that industry? I think those are the questions that get us extremely excited about. And we believe that you cannot get there if you don't make progress on the mathematical capability of AI.
Amazing. With that, we're at the rapid fire round. I'll ask a series of questions and would love to hear your answers in 15 seconds or less. You ready?
Yeah.
All right. Question number one. What's your favorite book?
Proofs on the book. There's the idea by Erdos that there is a book of all the most delicate mathematical proofs, and I enjoy reading it.
Amazing. Which historical figure do you admire the most and why?
Alan Turing, I think he really bridges theory and applications, and especially in the time where very few people believed that was possible. Also, a very high stakes situation, the war.
Yeah, yeah, yeah. What's the one thing about mathematical AI that most people don't get?
Yeah, it is the only domain where you can do conjecturing and do, conjecture, prove, and discover with consistent verifiable signals, like without sort of messy real world data, right? Unlike, say, self-driving or robotics, you need to actually go out there to get
Right,
those data and discover. Math is the perfect sandbox for self-improving AI.
right. What separates great AI products from the merely good ones?
I think the great ones actually compound things and unify things. So you can do a lot in it. It should be a frictionless, delightful experience. And I think it also should teach the user something that they haven't quite thought about, but then just feels like magic when you try. I'm like very of the Steve Jobs camp.
Right. What have you changed your mind on recently?
Um, I was pretty averse to caffeine before. I think that was like a drug. Now I have embraced it. Probably thanks to founding Axiom.
Yes, welcome to the world of caffeine. It's going to be a lifelong friendship. Um, what's your wildest AI prediction for the next 12 months?
Next 12 months, I think we are going to see an AI mathematician solve a really hard problem. I don't want to say necessarily Millennium Prize problem, but I think that AI for mathematical discovery is going to shock the world.
All right. All right. Final question. What's your number one advice to founders who are starting out today?
I think you really need to build something extremely hard. Like pick the hardest problem you can think of. I know that with AI, a lot of things could feel like great opportunities, unlocking things that haven't been done before quite easily and conveniently. But I think to build a generational lasting business, you really need to pick on something that is very hard because hard problems attract talent like a talent magnet. People want to work with the best of the best on the hardest, most stubborn problems. So I would say build something that is very hard. And I think Lisa Su from AMD also gave a similar advice that I took to heart. Build
All right.
something very hard.
Amazing. Karina, this has been a brilliant, brilliant discussion. Loved the insights, what you're building, just the sheer ambition of what you're building is exciting. So thank you so much for coming on to the show.
Thank you so much for having me.
All right.